Okay, so let's look at the meridional structure in winds, which essentially comes down to meridional overturning circulation in the atmosphere. It's great to start with the original Hadley idea, the schematic he created. Way back in 1735, the cell is named after him, obviously. His great accomplishment was to realize that the rotation of the Earth was affecting the winds, especially the trade winds. Trade winds had been used for sailing across the oceans for centuries, have been used by ships for centuries. So during his time, it was already past the age of discovery several centuries later. And his idea was that the Earth's rotation creates westerlies because the angular momentum is picked up from the surface into the upper atmosphere. So here you are looking a longitude, a latitude plane. So you're going from the equator towards the pole on the surface. So the sphere is basically here. So the upper level winds, he argued, should be westerly, which means coming from the west, because Earth is rotating from west to east. And he imagined that the pressure gradient then from the tropics to the poles would send kind of rings of air going from this zonal circulation bands towards the poles. So he imagined one big cell going from the deep tropics all the way to the poles, and the air sinking at the poles and then heading back towards the tropics to complete the cell. And then he figured out that there would be westerlies at higher latitudes and easterlies at lower latitudes, the trade winds, even though they're actually northeasterlies and southeasterlies, as we will see a little bit later on. Many ideas have come along after that, people arguing that actually as the sun goes east to west and the earth goes west to east, there are daytime and nighttime pressure gradients, and wind tries to follow and cannot keep up, etc. Then people have come along. Coriolis effect was discovered exactly a century later in 1835 by Gustav Gaspard Coriolis in a formal way, but nonetheless the impacts of rotation was already known to people like Hadley, at least. So the idea was about conservation of momentum. Obviously we know that this is not exactly true, but the thought process was already established. As it turns out, even now we don't have a completely accepted theory of Hadley cell. There are some very elegant theories, the famous Held and Howe model, and then many additions. We will see some of them a little bit later on. This is a figure that kind of summarizes the meridional circulation cells. So you have the northeasterly trades and southeasterly trades converging into the intertropical convergence zone, which is not shown here, and you have southwesterlies and northeasterlies, so polar easterlies and mid-latitude westerlies. So you have the rising motion, the convection that we've been talking about in the deep tropics with the maximum warming, evaporation, rising air, condensing, convection, clouds hitting the ceiling, going poleward in the zonal mean sense. We will see that there are also zonal circulation cells later on, but nonetheless in the zonal mean sense you have the Hadley cell, which is shown here as the convergence and the rising motion, and the cold poleward flow in blue arrows, and there is a high pressure here pushing air out towards low latitudes, and you add Coriolis, which we haven't formally done, but I'm sure you have heard it before. Plus, I have a module in my other oceanography course that you can look at on Coriolis in case you are not already aware of it. So that creates a so-called thermally direct cell related to the high pressure, cold temperatures, polar easterlies, and divergence, which meets the sinking air diverging at the surface towards the tropics and towards higher latitudes. So there is rising motion here in the subpolar domain. So you have a direct cell here that's going this way and an indirect cell that's going this way. So you can think of this as a kinematic cell. So this is a gear, that's a gear that are thermally directly forced, and this cell is kind of connecting the two gears with an indirect circulation. There are lots of details here that we will not go into, unfortunately, in this introductory course, but nonetheless, this is the Hadley cell, that's called the Ferrel cell, and that's the polar cell. Okay. In reality, if you look at the meridional overturning stream function, another thing we haven't actually defined, but actually the flow is always tangential to lines of constant stream function values as shown by the arrows here. So this is showing the annual mean meridional section of the zonal and vertical velocities. So you have the rising air in the low latitudes diverging, so positive here, negative here, positive here, and negative here, sinks, the Hadley cell sinking and converging back, and you have weaker Ferrel cell and a very weak polar cell. So you can see that winter and summer in the northern hemisphere will move the whole system with the radiation and the energy, because remember, these are part of the energy transport, lower latitude to polar energy transport. And when the sun is in that hemisphere, the equator to pole temperature gradient is going to weaken, so the energy transport required is going to be less, and so on. So there is a direct relation. Plus, when the sun is in that hemisphere, for example here in the northern hemisphere, the maximum heating and maximum rising are going to be in that hemisphere. So you can see that the entire stronger part of the Hadley cell is shifted here and shifted back here. So this is the boreal winter month when the sun is to the south. This is the boreal summer month when sun is to the north. Okay, and there is corresponding changes in the weak Ferrel cell and the polar cell. So we will look at this again with more details, but essentially when we look at the zonal mean meridional structure of the winds, the zonal winds are very strong. Meridional winds tend to be weak. Vertical velocities, we said, are already pretty weak because we said hydrostatic balance is generally valid. You can also think of the impact of rotation. So since Earth moves east to west, rotational effects are going to allow zonal winds to get stronger, but to cross latitude lines, you are going to cross Coriolis effect. Coriolis effect is zero on the equator, increases towards the poles. So meridional velocities are also constrained by the rotational effect, so the zonal velocities tend to be very strong. So if you want meridional transport of energy and you say zonal currents, zonal winds are strong, then how does the transport happen? Essentially in these kind of cells, but when you go to higher latitudes, you will need something called eddies, and we will see what that is just in a little bit. Okay, so a little bit of a hand-wavy explanation, but nonetheless they are important, and you can look at them carefully. So I'll show a few more figures to cement the ideas a little bit more, but just carry the concepts now, and we'll add the dynamics as we go along. So that's meridional overturning, Hadley cell, Ferrel cell, and the polar cell.